Great. So good morning. So my impression of you guys is that maybe 20 to 30% of you are coming from the statistical background, and 70 to 80% of you are coming from either a climate modeling, meteorological, or hydrological background. And I think you've noticed that as speakers we tend to there tends to be different languages that you use when you come from the stats background or the modelling background. So I work in a group in the UK Met Office in the Hadley Centre that works on climate projections for the UK. There's a core group of five of us, but we've been as big as about 9 or 10, and we're a mixture of statisticians and climate modelers. You may have found that some of that language barrier across those two disciplines a challenge this week. It's still a challenge even if you work in that environment for 7 years. So, I'm going to give a talk about how we've done climate projections for the UK. It's using a full probabilistic approach, so we'll touch on many of the toolbox subjects that we've done earlier in the week. So my role in the group is I'm a climate modeler, so I'm definitely coming from the modeling background, but I'll try and give you an overview of the whole framework. There's lots of people involved. There's a lot of work. We were involved in the projections. We started spinning this up in 2002, and we delivered probabilistic projections in 2009. At our peak, we were using 60% of the 34th largest supercomputer in the world to do the simulations. So there was a big investment from computing resources, and there's a big investment in terms of time. So I think this is hard. Lots of the things we were doing are very pragmatic decisions. You have to make decisions, and so I'm going to try and give you an overview of the whole thing. I'm actually going to give you 4 talks, 3 short ones and 1 longer. So I want to give you, before I start about the climate projections and what we did for UK CP09, I want to talk a bit about the context for climate projections in the UK and why we give climate projections. I'm then going to spend most of my time talking about how we applied many of these areas we've covered so far previously in this workshop. We've touched on how we applied them in this specific case. And then I want to talk a little bit about user reception, because when you're providing probabilistic information to users, some users find that much easier to deal with, and for others it's more challenging, and there are things we weren't expecting in providing that data. So I want to discuss that briefly, and at the end, if I have time, I'm going to talk a bit about how we're looking to update projections in the future. So I'm going to turn this around. So national climate projections have been carried out in a number of countries. So I'm just showing a graphic here from our own. So this is the UK ones on the far left. This is the Swiss projections that came out in 2011. This is the Dutch ones, which first came out in 2007. We're updating to 2014. So there's a fairly long history of using scenarios as a way to kind of inform decision making and planning. So I'm borrowing some slides from Suraj Desai, who's based in Leeds in the UK, I thought there was so all the slides which have University of Leeds, Suraj has contributed. So the first climate projection that we could trace back really was this paper that Tom Wigley led in 1980. So he gave a climate projection for the future, and it was fairly simple, but he was using differences in observed patterns and scaling them up. And the key part of this, I guess, is climate projections are about providing information about plausible changes in the future. What are plausible changes in future climate and what do they look like. And that gives us a starting point to start to think about how you can respond to that, or design infrastructure around that, or adjust, I guess how you start to respond to that. So there's so this one paper really kicked off the conversation in the climate community about how we provide climate projection advice to users. So we started to see more papers in the literature in the 80s and 90s. In the UK, our first climate projections were delivered in 1991. There was a chapter in 2011 specifically about how you generate and come up with a climate projection on the national level. And our first probabilistic climate projection really came out in 2009. So this is a map of a chart of our different projections. So our first ever projection in 2009 was non-probabilistic. There was no data for users. It was an advice document which kind of looked at basic maps of changes over the UK, and this progressed. So in '98, we used our flagship climate model at the time, HADCM2. But it wasn't really to UKCP 02 that we started providing data for end users to use. So there was from this point onwards, we had data portals where people could download and access the raw data from the projections. So this was all a single model study based on one model in the future for 4 scenarios, and there was no estimate of uncertainty. And it really wasn't until 2009 that we moved to a probabilistic way of presenting that information. So this is our 91 report. So in 2009 we had a 5-chapter report, and the central one here is what I'm talking about today. It's the probabilistic climate projections for land, and we had a similar one for the marine sector. But part of this whole process is also documenting what are the observed changes that have happened in the UK, and that information is seen as important as the projections for the future, because it gives you some idea about your vulnerability to. So for many users, being able to assess your vulnerability to current climate and current climate variability is your first step in terms of before you can look at how you respond to future changes. And that's particularly true when you start to present probabilistic information. So when you present a single scenario to end users, if you just have a single model projection for the future, it's very easy for people to look at that projection and say, okay, temperature's gone up, rainfall's gone down this season, this is going to have this impact on my business, or my river management system. Or but when you start presenting probabilistic information, before the users can even use the data, they have to be aware, be able to assess their own vulnerability to climate, and that means that they have to be much more nuanced before they can use the data. Okay, so I'm definitely loud now. So I guess a lot of the demand. So UK climate projections have bedded down in the UK, and they're seen as a central part of the planning process. So there's. So now if you plan new infrastructure, you have to show your infrastructure is robust to potential changes. So if you're building a nuclear power plant in the UK, you have to show that your nuclear power plant is going to be robust to, I think there's some very large return period, but 1 in 1,000 year events, and that's part of the planning process now in the UK. There's a large research demand, so research in other sectors are kind of linking back into the climate into projection systems. So if you're looking at the water use resources, they now refer back to the national UKCP 09 data, and there's it's now in the Climate Change Act. So there's the adaptation reporting power from 2009 says that the UK CP09 projections are likely to be a useful tool for some organisations in undertaking the assessment of their risks for climate change. They will allow decision makers to consider the range of possible future climates, as well as estimating the uncertainties surrounding these changes. So this was an act read out in Parliament in 2009. We now have a 5-year rolling climate risk assessment process in the UK, and so the probabilistic climate projections are a key source of evidence that feeds into this process. So I guess all I want to say really from these slides is that the probabilistic climate projections are becoming embedded in how we think about climate change adaptation in the UK. So that was a bit of a UK-focused context. There's a much wider international context. Come the other side. So in the first column here, you've got our first report in 1991, going down to the probabilistic projections in 2009. In Australia, there's been a long history of providing climate change projection advice. So the 2007 included non-probabilistic and probabilistic assessment of climate change risks over Australia. This was updated earlier this year, actually. The Australian climate futures. In the US, I'm less familiar with the US scene, but there are various national assessments of climate, so more qualitative. The Dutch have taken a scenario approach, which I'll talk a bit about tomorrow, where they look at scenarios which sample some kind of underlying uncertainty in projections. The Swiss have a very comprehensive national assessment of climate change. So I just want to point out that there's a lot of work going on in this area internationally. Right. So I'm going to skip through this last slide, and so I want to really talk about the UK climate projections. So far this week we've heard about various tools you have in your toolbox. So we've touched on Bayesian probability. We've looked at surrogate models and emulation. We've started talking about structural uncertainty. We've had discussions about designing experiments. So I'm going to touch on all these areas and how they relate to what we've done in terms of climate projections of the UK. So a lot of what I'm talking about has a very strong UK focus, but in principle, the same methodology that we're talking about here could be applied elsewhere in the world. So I want to just give you. So I think that overview is important in terms of kind of showing you how these tools could be used in a projection setting. So I think it's a very hard problem. I don't anticipate that most people will go away from this workshop and start applying these approaches in a probabilistic sense tomorrow. So on Thursday, I've got a 40-minute talk where we'll look at non-probabilistic approaches you can do with CMIPS models without going down this route. But today I'm going to focus on what we've done. Just to go back to the climate projections in 2009. So there was a single model. It was the Hadley Centre HCM3 model, and we provided maps and data for 4 scenarios in the future. So what I'm showing you here is the change in rainfall for the 2080s under a business as usual scenario, so the A2 scenario up here, and the reds show a reduction in rainfall, and the magnitude of the red is how steep that reduction is. So we're projecting up to an 80% decrease in summer rainfall in the UK by the 2080s for this scenario. So this is what we did in 2002. And I guess the user response to that was, that's great, that's interesting, but how do we use that information given that there are all these other models that other modelling centres have been working on at the same time, which instead of projecting one change, project a whole range of changes. So how do you use information from one model in the context of that wider uncertainty? And that's really what prompted us to move towards a probabilistic framework for presenting climate change information. So this is what we tried to move towards for our 2009 assessment. Okay, so the 2009, so what I'm showing you here is a comparison between the earlier single model projection and the probabilistic, and it's illustrating the additional context that there's an uncertainty estimate gives you when you're making a climate projection. So in most cases, the 2002 projections lie somewhere inside the probabilities we went on to produce in the probabilistic assessment in 2009. This is an example where it was more extreme. So in 2002, we suggested that over much of the UK, rainfall in the summer would be expected to decrease by up to 70 to 80%. So quite dramatic declines in rainfall. When you look at that in a fully probabilistic sense, the central estimate was still for a decline in rainfall by the end of the century, but of a less dramatic magnitude. And when you compare the range you get across the uncertainty estimates, the previous 2002 projection that you've been using to base your decisions on was much closer to the lower 10 percentile of the probabilistic distribution. So it was still plausible, but less likely. And it could be that there could be very little change in the summer rainfall. So this probabilistic information really gives that wider context to the uncertainties that we were lacking in 2002. So the projections were driven by user demands. So this is quite so when Duan talked about applications of uncertainty on Monday afternoon, he was thinking about the calibration problem. So how do you design experiments to come up with your best estimate for your model or your climate? The climate projections our climate projections were motivated by, we were interested in the tails as much as we were interested in the central estimate. So we want to know what's plausible, even if it's less likely, because that can also inform end users' decision-making process. There was the users wanted very high resolution information, perhaps higher resolution than you want to give them, or you think has any value in giving them. So some people want data down to 5 kilometers, or on the river basin level. They also wanted to know multivariate information, so it wasn't just one variable. They didn't want to know just how temperature changes in their particular town. They wanted to know how temperature might change with rainfall or winds or humidity. So we wanted to come up with a system which was able to capture that information. So the ingredients to this projection system relied on running large numbers of climate models to try and explore and assess the modelling uncertainty and how future climate change can change. It required the use of statistical tools, emulators. We used observations to downweight the less plausible projections. And we talked about structural uncertainty yesterday. We made a pragmatic decision to use other climate models from CMIP3 in this case to try and assess what are the structural limitations of our own models. So I'm going to go through each of those areas in turn and just talk a bit more. If you're not interested in a particular area, you can switch off for a bit and come back. So it should be quite modular, this bit of the talk. So this is a really nice map. So what I'm showing you here is a map of rainfall changes in the summer from 208 different climate model simulations. So each of these climate model simulations, we perturbed 31 uncertain parameters in the climate model. And you can see that so by the end of the century, there tends to be a moistening pattern above the UK, a drying pattern below the UK, and the UK sits on some threshold between the two. And individual simulations disagree. They largely agree on that pattern, but they disagree on the magnitude. So this model up here has a stronger drying in the south. This model up here has a weaker drying. And so by exploring these uncertain parameters in the model, you can, in some sense, explore some of the uncertainties in these projected changes. But there are exceptions. So this model down here has a very different pattern.
How did you sample the parameter space?
It's a very good question. I'll come on to how we sample the parameter space in a tick. So
what's the year for projection?
There's no error in this. So all I'm showing here is the raw climate model projection. So each of these maps is an individual climate model. So we haven't assessed any of the errors yet. All this shows is the range of possible model responses over this region in the future. There was so the global model is so we have a global climate model which is 2.5 degrees by 1.25 degrees, and then we use regional climate models to downscale that to the UK, but I'll come back to that in a tick. So I didn't think it was a downscale, but if it is the GCM, it looks very high resolution. So we produced this plot in 2007, so some of the details I forget. So I'll come back to resolution and downscaling in a tick. It's very pragmatic. So we're still working out how to do this. All I'm showing you is one approach to the probabilistic assessment, and we had to make pragmatic choices about how we sample the modelling uncertainty. So we considered the multi-model ensembles, and there are some advantages of these ensembles in that they explore a wider range of structural uncertainties than a single model where you perturb parameters. However, I'm going to step away so I can read this. The multi-models have some kind of interdependence, which is known about, but not completely. So they share common code, they share common oceans, common atmospheres. They're also individual modelling centres' best estimate of the climate, so they're not designed to sample the wider uncertainty. There's a lot of diversity. Some of them have a full aerosol cloud interaction processes, some of them don't. Some of them have chemistry, some of them don't. So they kind of, some of them are high resolution, some of them are low. There's a range of processes which makes them difficult to interpret. So we ended up using perturbed parameter ensembles of our model because so the advantages from our point of view is that we could come up with an experimental design designed to sample the broader range of uncertainty. We could construct statistical models based on those climate models that that were able to emulate what all possible combinations of our climate model would have done. And because we could do that step, we could then use observations to look at which parts of that model space is more or less likely. But it's very pragmatic. It was actually 31 parameters. Before we carried out these climate model experiments, we spent a lot of time talking to model developers to identify which parameters were important for the response to the model, but also uncertain, and what were the plausible ranges for those uncertainties. And then we ran more than 300 climate model simulations for present day, and an idealized experiment where we looked at the response of the climate to a doubling of CO2. So this is just a schematic to kind of show you the different tools. So on the left here, you have a histogram of global average temperature change for the 300 plus climate model simulations we did. So these models disagree on the magnitude, and they range from just below 2 degrees to, you have a few, one out here at 8 degrees. So they explore a range of future sensitivities to carbon dioxide. So this is where most of our computational resources went into this part. I come back to the experimental design in a tick. Then we used a much smaller sample of 17 transit runs, so these capital oceans, to look at the time evolving change. So this is the historical period along here, this is global mean temperature, and this is the future period, and they explore a range of future changes in the global mean. And we knew the relationship between these 17 fully coupled runs and 17 members within this 300.
Something different, but before you do the runs, how long do you calibrate?
So in the slab, these are slab models, these are idealized models, slab models. So we ran them for about 45 years to set them up, and then you have a 45-year control and double CO2. Whereas these ones, they were spun up for, depending on the model, between 600 to 1,200 years of pre-industrial simulation to get the ocean into balance with the atmosphere for each parameter set, which is why there is only 17 of these. I mean, in an ideal situation, you would want to use the fully coupled model to explore your uncertainty, but the computational cost of doing that is immense, so you have to think of ways you can get at this time-evolving information without having to sample your whole space exhaustively in this mode, which is why we kind of do the equilibrium sense. I think we're thinking about repeating this exercise today at the moment, and we're going to update projections in the next 3 years, and we're trying to see if we can do it in a fully coupled sense, because you avoid additional uncertainty you get from going from the equilibrium sensitivity tests to translate that. So if you can actually do all your exploration in fully coupled sense, then you reduce some of your uncertainty in your projections that way.
Speak up.
Thank you. So please keep saying that to me. So there are 3 bits of information from the modelling. There's the very large ensembles looking at the sensitivity of the climate system in an idealized sense. There's a much more limited exploration about the time evolving, and we use a relationship between these 2 sets of models to be able to build a statistical relationship between how an individual model in here would map onto the time evolving pattern. And then we use a 25-kilometer regional model to downscale this information. We only have 11 of these. We started off with 17, but we have 11 of these, and that gives us a relationship between the global and the regional, and and we use that relationship to downscale the larger information to the UK scale. So all the statistical work is done on this. All the evaluation against observations, all the building of emulators, which I'll come on to in a tick, is done on this large ensemble. So we wanted to know how these models would map onto the time evolving, and so we chose these 17 to span the range of sensitivities. So we have some of these models are sampled from models at the lower end of this distribution, the middle, and the upper part. But we also wanted these to be plausible models. So some of these models are ruled out as implausible or not very plausible. And we wanted these 17 to be reflective of the models you keep in this pack. So we spent some time trying to select that. So just to show how well this perturbed parameter ensemble does versus the multi-model ensemble, I'm going to show you 2 slides here. So this is the CMIP-free multi-model ensemble and its estimate of temperature change to a doubling of CO2 in December, January, and February. So this is the mean pattern from the multi-model ensemble. This is the mean pattern from our perturbed parameter ensemble, and you can see they share much of the same structure. There's a hint that this is slightly warmer in the mean state. And on the right-hand side, I'm showing you the standard deviation from both ensembles. You can see that the standard deviation of the perturbed parameter ensemble has similar structure and similar magnitude, if maybe slightly smaller than the multi-model. This gives you some grounds for confidence that your perturbed parameter ensemble is exploring the wider uncertainty in the European region where we use this. This is not true for all regions. So we've looked at Southeast Asia, looked at Vietnam, and our ensemble is a much smaller and different part of the multi-model space, but it's an important test.
That's true for precipitation?
I'll show you that now. So this is precipitation pattern. So this is the multi-model. This is and this is our perturbed parameter ensemble. You can see there's a very similar structure of moistening in the north of Europe, drying in the south of Europe, and there's a very similar structure to the variability across the ensemble. Again, the multi-model is slightly larger, so there's a bigger standard deviation, but there is a similar structure. There are differences, so there's a stronger drying over Spain than you see in the multi-model. There's a stronger moistening over Bergen in Norway in the multi-model than perhaps we capture. But there is a lot of similarity in both the mean state and the variability, and then that was an important part. If that's not true, then the perturbed parameter approach region really isn't useful in terms of guiding the uncertainty. So that's the modelling framework. I'm going to talk a bit about the statistical framework. To do the probabilities, we make use of a Bayesian approach to uncertainty developed by Goldstein and Rougier in 2004. And this approach is attempting to construct a joint probability distribution that accounts for the model parameters, accounts for the historical and future model outputs, so the relationship between the parameters and the historical and future response. It tries to account for where the true climate is and the observations of that true climate. And it also, and this is important, it tries to take account of model imperfections, which we call discrepancy. So I'll mention discrepancy several times in this talk, but what we mean by discrepancy is model structural uncertainty. And to do this, a Bayesian approach, you need a much larger sample of the uncertainty than the 280 to 300 climate models that we have. And so that's why we have to take on an emulation surrogate model approach to exploring that space. So this is kind of a summary of the whole methodology. So this is a histogram in green for the temperature change in June, July, August over the UK. So this is southern England, and so for a doubling of CO2, it suggests that it's going to be anywhere from not much different from present day all the way up to over 10 degrees warmer. That's the histogram. And the posterior PDF is the probability and density function, and this is what the PDF for the says for the same region. So I'm just going to break down how we go from the green to the PDF. So I've got a couple of slides talking about how we designed the couple model experiments to be able to emulate the response. So when we took that large ensemble of 300 sensitivity simulations where we're looking at the response of the climate to a doubling of CO2, we designed them in such a way you're trying to maximize the information about the relationship between individual parameters and the response to the model. And we used a Latin hypercube design, which was mentioned by a couple of speakers already. So here's two examples of Latin hypercube design. One is a bad example, and one's a good example. So the bad example basically takes, so each dot is a parameter combination for two parameters. This is the Cape time scale. So this is a parameter that controls the time scale of convection. And this is an entrainment parameter, which is a parameter which is the amount of ambient air which is entrained into convective events in the model. And in this example, each of these dots is a different climate model combination. And this is a really uninformative design, because if you find that these models are doing something very different from these models, you have no idea if it's parameter, if it's in the entrainment factor or the Cape time scale. So this is a more informative design, and you're trying to space fill this space so that you can use differences in the model responses between these different dots to tell you something about the individual parameters. And this kind of differs from the one at a time approach, which is more conventional, which are the red dots, which I'll come back to in a tick. So on my next slide, I'm going to show you the emulated response to the emulated error in rainfall from that's related to models with these two parameters. So this is two emulation approaches. These are the same two parameters on the bottom two axes. So this is the entrainment coefficient, and this is your Cape time scale. And you can see and what I'm showing you here is errors in 5-day rainfall for models taken from models which vary these parameters. You find the largest errors are up in this corner, so where you have a high entrainment coefficients and high Cape time scale, and the lowest error down in this corner. And I'll come back to the difference between the two. But if you go back to the previous slide, if you'd taken a one at a time test, so this is the central estimate, this is where you start, and you had done an experiment where you perturbed one parameter up here, down to the bottom, this parameter up to the top range, and down to the bottom, you wouldn't have picked up this structure. So you would have started off here and found that both parameters increased the error as you went to the high end, or center to the high end, but you wouldn't have realized that there are very large errors from the covariation of those two parameters. So the importance of this design is you're trying to explore the relationship in all parts of parameter space between the parameters and the response.
What's the default value on that?
So the default value is this central red dot here. So about just under 1.5 for for the entrainment coefficient, and Cape time scale about 4,000. So just a bit of information about the emulators. Sorry.
So here you show the error, the 5-day error.
Yes. Yes. This is a root mean squared error. Sorry. This is a mean squared error for the 5-day global error. Yeah.
And how do you initialize it?
So this is actually from a 5-day weather forecasting model, which is not part of the original UK CP09, but it's something we're doing now. But I can come back to this at the end if you like.
So it's not the same model that is used for the data?
In this case, it's exactly the same model we use for the climate prediction, but we're using it in a weather forecasting mode. And so the reason why that's really attractive is the weather forecasting simulations are only 5 days. You can do several through the year, and it's a very cheap experiment. It's a very, yeah.
Then you're favoring some parameter settings, because the data analysis is based on some model with some fixed data parameter setting. No?
So in the weather forecasting, we're exploring all the parameter space. So we have.
Also there you.
Yeah.
Also there you have all the.
Yes. Yes. This isn't part of UKCP09. This is just a slide I'm using to illustrate emulators. But this is what we're doing now. So we're using weather forecasting mode to inform on errors on the climate mode. But I'll come back to this at the end if I can. So the point I want to make at this stage in the talk is that we use a regression emulator. So we're regressing the relationship between the individual parameters and the response or the error or whatever the variable is you're interested in. But you could also use a Gaussian process emulator. So this is a Gaussian process emulator we've trained on the same data. And you can see that they have much the same underlying structure between these two. You get them, it's emulating the larger errors you get in this part of the parameter space in both cases. And you could use either. There are advantages and disadvantages of both a regression emulator and a Gaussian process emulator. Gaussian process emulator is much simpler to use. You can treat it, I'm sure Dave will not agree with this, but you can treat it as a black box in many senses, and you can apply it. And the regression emulator, on the other hand, you have to think about it a lot before you do it, because this is computationally much, much faster than this, which is one reason why we use it. The other reason we use it is that it fits the surface through the model space. And it's less sensitive to internal variability that you always get in climate models. So the reason why the Gaussian process emulator is lumpier, if you look at the surface, there are ridges and valleys as you go up. And that's because the Gaussian process emulator is forcing it to go through every single GCM point. And so if you have a strong El Nino in one year or a strong weather event in another year, it's forcing it to, it's saying that's the climate response. It doesn't differentiate between the two, whereas a regression emulator will go through, it will fit the surface and is less sensitive to that internal variability. But the downside is you have to think about the relationship between your parameters and the response. So is it linear? Is it polynomial? Is it some covariation between parameters? And you have to explore those. So it's much less of a black box tool. So that's a specific bit of information that you might think about if you're doing this at home, but otherwise you can ignore. So this is just a quick schematic in 2D. So I've shown you some in 3D. I've shown you some 2D plots, but we have 3 parameters here, and the light blue dots are individual models. And the small coloured dots are your emulation. It enables you to emulate the response surface across that 3D space, and so you can capture regions where you have stronger responses or weaker responses. So what your emulator does is it enables you to populate that wider space and talk about how about any possible model combination within this space would respond, both in present day, so you can compare it to observations, but also how it responds in the future. What we're doing when we're emulating, we're not actually emulating the relationship between an individual parameter and an individual variable. We're emulating a principal component or an EOF of the climate model. So I've got 2 slides on this. So this is quite involved, so don't feel you need to engage with these 2 slides if it's not your thing. But what I'm showing you here is the leading principal component across these 300 member ensembles for a number of variables. So I'm showing you winter and summer, rainfall changes, rainfall, shortwave radiation, shortwave cloud forcing, longwave cloud forcing, and longwave radiation, and relative humidity. And this principal component this is the first principal component. So it's how these 6 metrics, 6 variables vary most across your ensemble. And so you look at the top right plot, you can see this is how these maps project onto each individual ensemble members. So a lot of them are quite positive, they disagree on the magnitude, some of them are negative, but if you multiply for a given ensemble member this value by these maps, then that gives you the first component of that response. If you do this, we do this for the first 6 principal components of the climate system, and you can reconstruct the majority of the climate, the simulated climate response of your model. And the reason why you do this, rather than emulating an individual variable, is it keeps the multivariate information. So as temperature, as humidity changes, you keep the relationship between humidity and precipitation and cloud radiative forcing. And so you can reconstruct, by emulating the principal components, you can reconstruct the spatial coherence of how the models respond. So this is my last slide on the principal component emulation, and this is just to show this is the first, second, third, fourth, fifth and sixth eigenvectors for these principal components, and each of the dots, the dark blue dots, shows the GCM runs we ran. So this shows how each of those principal components varies across the ensemble. The light blue shows the multi-model CMIP3, so you can see that they're exploring similar uncertainty spaces. It's a hint that we explore more out here in eigenvector 1, but the multi-model spans, we can span the multi-model range. The black lines are our probability distribution, and the important thing is the observational point, which you can do this for the observations, is in the pack, is in the range of models, and that's an important sanity check that you're doing something that you can actually compare to the observations. So this is where we want to go. We want to go from the raw model output. So this is Northern England temperature in March at 1.5 meters. We want to go from the more raw model output in green, and we can emulate that. So that's our red line. That's what we call the prior, and we want to weight that by the observations to produce the blue line, which is our probability of change in March temperature in this plot. So the blue line is where we want to get to. So what we're doing is you're combining your log likelihood of a model given the observation with its prior expectation that's there. So if you go back to this plot, the green histogram can be emulated to give you the red line. So that's your prior expectation of what March temperatures are going to be in Northern England in this plot, and then you're combining that with the log likelihood information for an individual model given the observations.
For the EOF, so you take the EOFs of the observation and the model separately, or do you project one on the other?
So you're taking the EOFs for the models, and you're emulating the EOFs, and then you're using those to reconstruct. So once you've emulated all of your 6 first principal components, you can then reconstruct for any given model what the climate response looks like in all those variables for present day and the future. You can use the present day then to compare directly with the observations. So this is the log likelihood function, and the important thing here is you're comparing the model with the observation. So that happens twice in this equation. But this is a very important. So this is a matrix calculation, but it's the V matrix which is important. I want to highlight here. So this V matrix involved in this model observation comparison contains the information about the uncertainty in the observations, contains the information about the uncertainty in the emulator, which is really important because the emulator tells you about the model space, but it's not, we can quantify the imperfections in that process. But it also tells you about the discrepancy or the structural model error, and I'll come on to how we identify that. So I just wanted to give you a quick. So that's the mathematical way of looking at the weighting. I just wanted to give you a more graphical way of looking at it. What I'm showing you here are 10 random draws. So this is the emulated climate sensitivity drawn randomly from 100,000 different emulations. And so this is the climate sensitivity for doubling of CO2. And you can see that and each of these curves is the emulated response for a different part of possible parameter space. And so there's an uncertainty there. The uncertainty comes from the emulation uncertainty, but also from the internal variability, which so most of this width comes from the impact of internal variability in limiting your ability to know this emulation perfectly, but also the emulation error. But the basic point is you've got 10 different emulations of climate sensitivity for a doubling of CO2, and what the weighting is doing is it's comparing each of those with the observations and giving more weight to the ones which are or less weight to the ones which are less consistent with the observations. And so you can see how that structure, the PDF, is kind of emerging. So that's, statisticians probably don't like that way of presenting it, but that's a kind of way that's more accessible for me to think about it. All this work I've been talking about has been talking about how you emulate in the sensitivity state. So what is the climate response in present day and for a doubling of CO2, and we do the emulation and your weighting in the present day here. Then we do what we call time scaling, which is translate that into a time evolving change globally. And then we use the regional climate model relationship to translate that information down to the UK. So that gives you the PDS of the UK. So I just want to talk a bit. I've got one aside, and then I'm going to come back to structural model uncertainty. So all the work we did when we did UK CP09 was to look at the uncertainties in the atmospheric physics response. So when we started this work, the expectation was that cloud feedbacks particularly, but convection, boundary layer processes would be the most important uncertainties in the climate system. And so we wanted to devote most of our resources into understanding those uncertainties. I did a number of other experiments looking at aerosol uncertainties, carbon cycle uncertainties, and ocean physics uncertainties with Matt Collins on the ocean physics side. So I'm just going to give you an aside here. This is so one of those three was actually very important for the global mean temperature, which was the carbon cycle. So I'm showing you two plumes here based on an atmospheric physics ensemble and a carbon cycle ensemble. And the blue plume is the range of global mean temperature from the historical and future periods from the atmospheric physics uncertainty, so that's cloud, boundary layer, convection processes. And the green plume is the range of global mean temperature you get from uncertainties in the carbon cycle. So that's when emissions of CO2 go into the atmosphere, do they go into the land? Is the land a net sink or a source, or how much does the land take up in the future and the present day? And what you can see is the spread in the green plume is comparable to the spread in the blue plume. And so what we do in our projections is we factor that into the projection system. But we only sample 17 realisations of that. There's no observations of carbon cycle processes. Because we had only 17 models, you couldn't make any probabilistic statement about which of those 17 was more realistic. If we do this again, we would want to sample the carbon cycle processes as thoroughly as we sample the atmospheric physics processes and apply the observations in the same way, what observations they are in the same way as you would in the atmosphere. So that was just an aside. So this is a kind of schematic of the process of the whole methodology. So we've been talking about this step up here mainly. So you've got a large GCM ensemble here. We're going to talk about structural uncertainties in the tick. We're using observations to weight that and surrogate models to emulate this. We then translate that into time-evolving information via a simple climate model, and we factor in the uncertainties from the other components in the system into that simple climate model. And then we downscale that to a regional climate. So that is UK CP09.
But then you're assuming that you can have all the uncertainties by parameter theory. For example, if you change the resolution of the ocean, how would that impact this?
So that is an assumption, and so I'm going to come on to that now. So that's we're talking about how we can use other models to assess the limitations of this approach. Chris.
Most of the discussion has been about temperature and precipitation in a lot of this, but I rarely hear people talking about sea level rise and uncertainty quantifications.
So I'll come on to give an example of sea level rise in the planning for the Thames barrier a bit later on.
I guess my point is the discussion of the ocean heat uptake, and you're saying that only one of your ensembles mattered for temperature change. It looks like. Did the ocean physics ensemble have an impact on?
So we also factor in the impact of the ocean physics on differences in the ocean physics ensemble into this assessment. So that's coming in through this step. In terms of the ocean heat content change, surprisingly, we found when we perturbed the ocean parameters, we went to the ocean process modelers, found our ranges. And we went away and we ran this experiment, and we found a very small range of ocean heat content changes as a result of the ocean physics. And so we went back to the ocean modelers and said, what's going on here? There isn't much going on. We expected to explore a much greater range of ocean heat content response across this ensemble. And they said, maybe we haven't given you big enough ranges. So they went away and gave us much bigger ranges. And we went away and repeated the same exercise again. And we still had a small range of ocean heat content changes. We actually explore quite a wide range of ocean heat content changes through the atmospheric physics ensemble. And what it looks like in this particular model is that the atmospheric wind field drives a lot of the ocean circulation structure. So differences in the atmospheric wind field were having a bigger impact on whether a particular model was taking up more or less heat in transient climate.
All the models from the IPCC or only the coupled one?
So far I have not talked about the multi-model ensemble at all. So in what I've described up to this point, I haven't discussed it, but I'm going to come on to that topic now. So structural model uncertainty we discussed yesterday afternoon, and it's come up in most talks so far this week, and there's been questions about it already. So this is a highly pragmatic choice, and there's no right answer, but we wanted to do something because doing something is better than not doing anything at all. So what we did is we used information from the multi-model ensembles, so that was CMIP3 at that time, and CFMIP ensembles, to try to estimate what was the structural response of those other models that we could not reproduce in our perturbed parameter approach. And so what we're doing is you're using your emulator of Hadley of our climate model to find the point in Hadley parameter space which is closest to a particular model. So if we were to take the BNU, if you take CCSM free from the CMIP free ensemble, you try to find the point in our parameter space which gave a present-day climate, or gave a present-day and future climate response closest to CCSM3. And then you estimated the errors. So you find that in some parts of the world those errors are very small, and in other parts of the world the errors were much larger. How am I doing for time? I'm doing okay. But you could use, so what you're doing is using the multi-model to kind of estimate what was the structure in other models in their present day and future response that you couldn't capture in yours, and you're adding that on to inflate the uncertainty where that was happening. And I'll give you some examples. So we did that for every single one of the multi-model ensembles, and we did that for the CFMIP ensembles, and so that gave you a distribution of errors at every point in time and space and variable, and we sampled that when we came up with the final distribution. So some examples of that process. So before I give some examples of that process, I just want to motivate why, in another context, taking account of a discrepancy is important. So, so when we first looked at weighting parts of parameter space, we came up with a large number of metrics for present-day climate, so present-day climatology, that we wanted to assess how well the model was doing. So each of these vertical bars is the range of errors for a particular variable across our ensemble. So so if you look at a particular bar, so this bar here is the shortwave cloud forcing, and the models have a very wide range of errors across that quantity. As if you look over here, you've got surface temperature. I'm too close to see it. Here we go. And you've got a much smaller range of errors across the ensemble. And because the log likelihood is proportional to the model compared to observation squared, the exponential of that, what you find is that the very poorly modelled simulations, so these variables up here, were having a much bigger impact on weighting models than the variables you are confident your model could simulate. So we have much more confidence of temperature than we do about mid-level clouds. The mid-level cloud is up here. None of the models catch a mid-level cloud, and yet this single observation was having a much bigger impact about whether you reject, downweight, or accept a model than global mean temperature was. So what we're, in a schematic sense, what you're trying to do when you account for discrepancy is you're trying to normalize them in a way. So you're trying to make sure that something like global mean temperature, where you're confident your model can do well, it has as much information as variables where you have no confidence, where all the models are getting it wrong. So this is a schematic. This is a schematic motivating why that structural, it's important to account for that structural uncertainty. Otherwise, you're making too strong statements. So this is another way of showing that using the actual model results. So when so it goes back to that idea that you have a range of climate models, and the observation is not one of your climate models. There are structural differences between your climate models and the real world that you need to account for. So if you don't account for it, you are too confident about which of your models can be rejected. So what I'm showing you on the right-hand side is the weights given to individual samples of possible Hansian-free climate models from a 50,000 member sample, and you can see that there are only a handful of models, so about 40 according to this metric, that contribute at all to the PDF of annual temperature globally, and as a result you have a very confident prediction of what the global mean temperature will be in the future. It's very peaked. When you account for discrepancy, you account for the fact that there is a distance between the real world and even your best model. The best model is not the same as the real world. You can entertain a broader range of models, so of the order of 400, and you have a broader and broader PDF. So when you account for the fact that there is a discrepancy between your best possible model and the real world, what that does in effect is it broadens your confidence about a future change in the future. So that's a kind of a wider theoretical way of thinking about it. This is how it actually impacts projections locally. So this is two examples, and the top one is typical, and the bottom one is atypical. It's unusual, but there are places where it happens. And this is what discrepancy is doing in these projections. So I'm going to come over to this side. So again, the green distribution is the distribution of from the raw model output. So this is what the models suggest that the March Northern England temperature will be at a certain point in the future. So the two lines I want you to look at. So the raw model output is in green, and then there's these black lines are the important bit. So what we've done globally is we've found the part of parameter space of our model which is closest to each of the individual CMIP3 models, and we've seen locally what is the error in predicting that CMIP3 model in present day and the future. And you can see there's an arrow from a square going one direction or the other. So over northern England in March, there's a spread of discrepancies in our ability to use these models to predict other models, and they either suggest it's cooler or warmer. And when you factor those all in, you get a very small change in the mean, but what you do in effect is you broaden the PDF. So that's a typical example of what accounting for the structural uncertainty does for most variables in most locations. Is it tends to broaden the PDF. Where it's more severe and it does more work, I'm showing you an example down here. So this was March temperature in northern England. This is March temperature in Scotland at the same time. And the difference is there's a bias in our model in Scotland in present day. Scotland has snow in March, where the real world does not have snow in March. And the other multi-model ensembles largely do not have snow in March. And so in a global warming scenario where you've warmed it up, you've suddenly lost a lot of snow and have a very large temperature change in our ensemble, which you do not find in the other multi-model ensembles because they have a more realistic present-day snow. So what the discrepancy is doing here, in almost every single CMIP5 model, you can see the arrows are going in that direction. They're going towards cooler temperatures. And it's saying that the structural features of your model are different from the multi-model and in a systematic way. And that's broadening the PDF in black, but it's also leading it to, it's pushing it to cooler temperatures to try and correct that bias, that structural limitation of your own model. So hopefully that gives you an idea about what it does typically and what it can do in some places where you have structural differences between your own ensemble and the multi-model. This is one last example, just as a wider discussion about structural uncertainties rather than anything we actually did in this approach. So we're interested in UK projections. We're interested in, therefore, the storm track about how low pressure systems come through and bring in rain and high winds. And this is a metric for all latitudes, so all longitudes for blocking. And the reanalysis, the observational estimate, suggests there's a much stronger blocking in the climatology in the region where the UK is, and most of the models underestimate that blocking. And so this is another example of a structural limitation of a model. So you might expect that to have an impact on projections in your region. And there's some work suggesting that as you go to higher resolution, for example, you can correct that underestimation of the blocking in this. So this is a section out from here. You can correct much of the bias in blocking in present day, and you get something much closer to the observation. So you really need to look at higher resolution models perhaps in terms of how you use those models to correct your biases in this region. So this is just, I threw this in as another example of a structural uncertainty to kind of widen it out. Okay, so final thoughts on what we call discrepancy, or what we've called in this workshop structural uncertainties.
Go back to the last slide. Would you, which downscaling help here?
Downscaling might help here if you found in your downscale model that you correct the blocking. So it's something you could look at. I suspect that the domain you're looking at, the storm track and the blocking is controlled by larger scale circulation, and that's going to be prescribed to your regional model.
I think it's very unlikely that downscaling will help, because it depends upon the structure of the emerging waves, and that is the guide of the global model.
Yeah.
The
Luke.
analysis seemed to, over a latitude, roughly corresponding to the UK.
Yes, that's right.
Right.
Yes. So I actually think it's more of an open question about what resolution does. So there are certainly examples where high resolution models are able to correct this bias. High resolution models can also exacerbate the bias in other parts of the globe. So I think there's an open research question about what resolution does to blocking, but it's something we should think about. So some final thoughts on structural model uncertainty. So what we've done is highly pragmatic. So what you really want to know is what is the structural error between your model and the real world. And what we've done is what is the structural uncertainty between our model and other multi-modeling centres. So that helps because there are structures there are limitations to our model that limit our ability to model other climate models. But there are probably common structures to all those models, for example, resolution, that we cannot sample in this methodology. So we're underestimating that structural uncertainty. The advantage of using the multi-model to estimate it are twofold. So one advantage is that you get some estimate of structural uncertainty in the future, which you can't use observations to do. So the multi-model gives you information about the past and the future. The other advantage, well, the other limitation of trying to use observations to estimate your structural uncertainty is that if you quantify your structural uncertainty compared to present-day observations, you can't then use those same observations to weight which models are more or less plausible, because you're using the same information twice. So that was another reason why we wanted to use the multi-model in a sense. But it's a very pragmatic choice. It's not ideal, but we don't know what is a better choice. So we want to be clear that you have to make some pragmatic decisions when you think about structural uncertainty in projection systems. Okay, so I've got 4 or 5 slides about sensitivity studies just to wrap up, and then I think I might touch on the users at the end. We've produced projections for the UK, and one of the things you can do is look at how sensitive some of the choices you make in your projections to underlying choices in your design decision. So I've shown you plots earlier where you have a prior. So this might be temperature in March or something. You have a prior distribution of model responses. You weight those by the observations, and you get some kind of posterior density function. So you get a prediction. And so this is combining the prior information with the log likelihood, and this prior is based upon sampling parameter ranges that we elicited from the developers of the model. So one of the things. So when we first did this. If you have a parameter A, and they've given you a range between here and here, we looked at what happens if you just considered all parameters within that range plausible. What happens if you did that, but also considered some kind of shoulder where you're tapering off, so you're not saying that this parameter is equally plausible to the center, that's not plausible at all. What happens if you assume some kind of function like this or this? Do those subjective decisions in how you explore parameter space have an impact on the projections? And that's what I'm showing you here. So this is June, July, August mean rainfall over England and Wales, and what I'm showing you on the left-hand side are the range of projections from taking a triangular trapezoid, inflated uniform, or uniform distribution for your underlying parameters. And you can see before you apply any observational weight that the 5 to 95% range varies a lot. So on the low end, so this is summer rainfall, you're suggesting there's a small chance of an increase of rain in England and Wales. You tend to predict a decrease in rain. But the lower limit can range from 45% to something like 70% or 65%, depending on your prior choices. On the right-hand side, once you combine that with information about which of those models are more likely given the observations, those upper and lower limits are much less sensitive to those underlying decisions about parameters. So this is a really good confidence measure. This says that some of the subjective decisions you have to make when you do this probabilistic projections are not having a strong impact on the kind of projected changes you're given for the UK. And I can do this, so this is annual mean temperature globally, and the upper limit is important. So before you apply the observations, you got to lower to an upper limit of somewhere between 1.5 to either just over 4.5 or somewhere up near 7, depending on the underlying decisions you made in how you sample the parameter ranges. After you applied the observations, that's a much more constrained range. So there is still some uncertainty in the upper range, but it's between 4.8 and 5.2. So you're much more confident. So this is an important sort of sensitivity that the priors aren't having an undue impact. This is percentage of summer rainfall, but the actual plots of a global mean temperature. Apologies. So I've got 2 more slides. So this is looking at which of the parameters are important, most important in different parts of the world. So once you've got this kind of methodology, you can look at these kind of questions. So these are maps. So you see that the entrainment coefficient is very important in the tropics. So there's the big blue areas in the tropics where you have strong convective events. So how much ambient air is entrained in convective events is the key parameter in tropical climate regions. If you looked at large parts of North America, for example, then you're looking at the orographic gravity wave parameter as being the most important. So how flow over the Rockies affects the circulation pattern is being explored by that kind of parameter. So it starts to give you some kind of insight in terms of what are the processing parameters that are important in different parts of the world. So what you're doing is some kind of variance comparison. You can use your emulator to look at how changes in individual models lead to a range of different responses based on the individual parameters. You can also look at the covariations between the two.
So the conclusion is related to the range of the probability.
It is. So again, it's sensitive to your range. So it's sensitive to whether you've elucidated the range which is a sensible range. So if one of these parameters has a range which is too large, then it might have an undue impact on this kind of plot. So you're right. So my final slide, looking at sort of sensitivity. So this is a more modern plot. So we've gone back and done the elicitation again. So this is 4 by 5. This is 20 parameters from the atmosphere, and we've gone back to the model developers and looked at what are the ranges. So so some of these ranges are still uniform. So this parameter here. Some of them are uniform with drop-offs at the side, and some of them are more informed. So you've got these parameters down here, which are some beta functions with truncations. And so in each of these parameters, we've sat down with the model developers and got them to talk about what do they think their prior expectation is on those parameters based on their insight from observations or model development. So that's the red lines. The histogram that's behind it shows the weighted histogram of after you've applied the observation or constraints. And you can see that for most parameters, the weighted histogram is very similar to the prior. So comparing your models with the observations has had no impact on your confidence about whether one part of parameter space is more important than the other. And I think that says that that parameter doesn't have a big impact on the climate, particularly the things that you're comparing with observations. There are some parameters, and there are only a very few parameters where that's not true. So one is the CAPE timescale, the convection timescale. The other one is the entrainment coefficient. And in both cases, you see that very high values, which you including your prior, are significantly down-weighted when you compare it with the observation, so that you're losing a lot of this density, and you're saying that combinations over here are much more likely. Similarly, you're ruling out much of the high end in the entrainment coefficient. So this is a useful way of saying how observations impact individual processes or parameters. Okay, so I've used up much more time. I can stop here and we can take questions. I can mention a bit about how users use data. Perhaps I'll stop here and take questions. I can do, yeah. I wanted, is that a useful use of time? So, okay, I'm going to skip through some slides. I'm just going to show you a couple of quick plots of what projections look like. So this is a multivariate plot about how Tuscan summer temperatures will change in the future, or St. Petersburg winter changes, and it shows you how the multivariate nature of the projection. So you can say something about both how rainfall will change and temperature will change as you go through time. So at the beginning of the century, you have some chance of having wetting conditions, but as you go through the century over Tuscany, you get this drying signal, and there's a covariance structure. So for the very warm changes are associated with stronger drying. And you can a similar pattern with St. Petersburg. So this data is being used to drive impacts models. This is an impacts model looking at crop yield over Tuscany onto the ensembles project. And so it's taking the 2040 to 2060 climate changes, and is suggesting that if you're in this region up here of low temperature changes and lower drying or moistening, you could have an increasing yield, but 86% of that prediction space suggests there'll be some reduction in yield of corn over Tuscany, of wheat over Tuscany. Okay, user reception. So we provided probabilistic projections, and they kind of there's a data portal. You can download the data. That data is being used to inform decisions and planning, building infrastructure in the UK. I just wanted to highlight 3 different users because they have very different ways of interacting with this data. So the first example is Natural England, so people who work with biodiversity in the UK. So their remit is to make sure that climate change is shaped by its wider remit for protection and improvement of the natural environment. Climate change is a major threat to the natural environment, its biodiversity, and the services it provides. And adaptation is essential to reduce risks as well as take advantage of opportunities that arise. So Natural England is very interested in climate change, and they're involved in planning for biodiversity and how you respond in the future. But they cannot deal with quantitative data. They cannot deal with a PDF. They have no way to handle a quantitative information. So they want a qualitative story, a narrative. Is it wetter, drier, warmer, so on. And so that's one kind of user. So another user was the Thames Barrier. So there's a barrier at the mouth of the Thames, and London sits on the Thames. And this barrier was put in there because when you have high sea level rise, and you have a large river flow, because it's rained a lot in the last week, those conditions can combine to flood London. And the economic impact of flooding London would be huge, so hundreds of billions to trillions of dollars. So what they've done is they've built this barrier at the mouth of the Thames, and so when you get very high sea level rise, you get storm surges in the sea, and you get a large river flow. You raise that barrier and you stop the water coming in. And when it was built, it was used once every couple of years, and it's been used. I think there's a record year where it was used 48 times 2 years ago. So they've been looking at how you do they need to upgrade that barrier, which would cost money? Do they need to build a barrage, something that's much bigger infrastructure, and that's much more expensive? So how do you make that decision? When do you need to make that decision? And they can use quantitative information. So this is their decision matrix. There's on the horizontal scale is magnitude of future sea level rise from 0 meters to 4 meters, And these are a range of different options they have that can cope with different sea level rises. The AR3 estimate for sea level rise was right down here. It was huge. It was about 4 meters. And so at that stage, they were convinced they would have to invest in the barrage, which was hundreds of billions of pounds to build, and big ecological impact. The upper end of the probabilistic, the upper end of the plausible range that came out of UKCP projections was right down here, below a meter. So by the time we got to AR4, we revised down the sea level rise substantially, and this is the upper range. So there are lots of other measures you could do to adapt to that kind of change. They also considered a second scenario, which they call the plus scenario, which is their new top scenario. And so there are factors in these projections that weren't accounted for. So at the time we were doing this, there was a increasing awareness that the West Antarctic ice sheet had a potential to be unstable, and that wasn't included in any of the modelling work. We didn't have the modelling tools to be able to assess that. So the H++ is an estimate of what is a high-end range from storm surges and river flow from the probabilistic projections, plus what you could possibly look at if the West Antarctic ice sheet collapsed completely in the century. So it looks like there are lots of other decisions they could make which don't involve a barrage you can do to kind of respond to that range of sea level rise. And what they're actually going to do is it provides a time scale that they can reevaluate these decisions as you go through, and as new information comes into the climate change process, they can update that. So it gave them a timeline about when they make decisions about, do they over-rotate the existing barriers, increase the levees. So this is an example about how people can respond to quantitative data. And the last one is a challenge for us. So one of the users that really wanted the data was flood defences in the UK. They really want to know where you need the defences, which regions are going to be impacted, where the risks are, how you build yourself out of it. But the kind of information they need is very difficult to provide at the scales they need it in. So what they want is spatially and temporally coherent data on the river basement level, both for extreme events, but also what happened before. So was the previous 2 weeks very dry? Is this, therefore the soil very dry or very wet? And so you want information that you can't provide from a statistical downscaling tool, which is what a lot of the high resolution data was. And you need a dynamical climate model to kind of do that. So this is really kind of motivating where we're going to go next. We're going to update the probabilistic projections, but we're going to try to have more climate model simulations with downloading tools to be able to provide that spatially and temporally coherent information at that local level. So 3 very different users, and so I think there is a need. Some users just need a narrative. They do not need data. They do not need numbers. They don't need, and certainly don't need probabilities. And there are certainly users that we found that can use that probabilistic information. And it's just been aware that there are different users in the user case. I'm way over time, so I will stop.